Hi everyone, and welcome to the second video of the course on large language models. This is part of the masterclass on building AI products. In the last video, we really saw how LLMs have been trained, not just through larger compute, larger training data sets, but also trained in slightly different ways in order to get to where we are with the ChatGPT moment, which is a combination of training base LLMs, that is using a large amount of unsupervised text from the internet combined with large amounts of GPU power to then create the base LLM. This was followed by the instruction fine-tuning step where you actually trained on a data set of question-answer pairs so that the LLM then knows how to respond to questions. And then in the end, we saw how you can adapt the text that is generated by these LLMs to align with what humans would expect through the step called as reinforcement learning with human feedback. Today, what we want to do, or in this video, what we want to do is dive a bit deeper into actually understanding how the LLM generates text. What is happening when each word is being generated? This is not very useful when you are just using an API, but it's very interesting to know as a strong foundation for what is actually happening under the hood. And I find it really fascinating because it helps me get a very nice understanding of what happens when you see a certain generated text from ChatGPT, how you might adapt it, and so on. So that's basically the goal of this video. This video also has an accompanying notebook, which you will find in the course material. So feel free to follow along if that's what you want to do, but you can also listen to the video and then go to the notebook as well. In order to kind of walk you through what is actually happening here, I try to create a sort of simple example or a situation. So let's imagine that you are creating a new product and are looking for ideas on what to build. Now, I'm a huge fan of Pokemon, so I've picked some Pokemon characters as the name of my startup. So you can say, hey, my startup's name is Vulpix, for instance, and you can actually go to an LLM, so ChatGPT, for example, and say, hey, Vulpix, which is the name of my startup, offers many direct integrations that allow you to build something. And then you can expect ChatGPT to kind of complete it, and you can use this completion as an idea for what you might build. Of course, the response that you get from ChatGPT will be very sophisticated. It has really been trained using the techniques that we discussed, like instruction fine-tuning, RLHF, and so on. But let's compare it now to a base model like GPT-2. So the link that I've provided here is something that you can open up on Hugging Face and actually write this to complete and look at the text that is that it provides as a completion, right? And that's kind of what we're going to look at today. So we are looking at the base GPT-2 model. So this has not been instruction fine-tuned and not been tuned using RLHF. It's simply a text completion model. And what we are trying to do is understand how the tokens are generated at each step of the way and what are the strategies that are followed there. I said tokens. What does this token really mean? Let's take a look at that. What you see here is basically the architecture of the transformer model. Transformer is a kind of neural network architecture that forms the basis for most large language models today, including the OpenAI, GPT 3.5, GPT-4, etc., etc. So that's what you see on the left. This is actually borrowed from a blog post by Jay Alamar. So I've also linked it in the slides, and you can also take a look there, and it has a really nice detailed explanation. While we're not looking to go super detailed into the transformer architecture itself, the most important part that I wanted to point out was these last two layers, which is talking about softmax and linear, and then the output, right? So in this whole architecture, you have input that is coming in. So in this case, the input text that we decided in the previous slide, which is Vulpix offers many direct integrations that allow you to build. So that's the input that is going in. And the LLM now needs to produce the output, which is nothing but complete that sentence, right? So it's doing next token prediction. Now, what is happening at this next token prediction is what is then the focus of this linear and softmax layer on the top here. And I have then blown it up, as you can see see on the right hand side to kind of show you in a bit more detail what is actually happening. So at each time step, right? So now this is where the idea of a token comes in. Each word is considered a token, and there is a sort of difference between a token and a text, but for now let's assume that a token is equal to text. We will clarify this further in the next video when we come to the project, but for now let's assume that a token is equal to text. So for every text that is produced, so that means that you have put in this input words, and then you have to get the next words, right? Each word that is generated, actually at each time step, you have a distribution, a probability distribution across the entire vocabulary of the transformer model, or of the last layers of the transformer model. So this is what you see here on the top, right? So there are words like complex, third, integrate, the, reception, brave, and to each of them there is also a probability value. So for instance, the probability value of complex in this case is 0.12, whereas the probability value of integrate is 0.02. That means that complex has a higher probability value than integrate at this time step, or at the point that it is generating this particular text, which means that it is more likely that the word complex is going to be picked as the token completion or as the generated text compared to the word integrate. So that is kind of how the LLM decides what is the next token to produce. These values are nothing but the probability distribution, and this is therefore each word in the vocabulary of the LLM gets a probability distribution at each token generation step or at each text generation step, right? We said text is equal to token. And then the word that has the highest probability gets picked. And obviously that means that the model is kind of deciding what is the most obvious next word to come, and it gives that a higher probability, and then it picks that. And that's kind of how the text completion happens. So at each time step, you kind of say, okay, what is likely, or what is the one that has the highest probability? Then you generate that token. And then this token is fed back into the input again, right? So for instance, in this case, the highest, the word with the highest probability is complex. So it's likely that complex will be the next token. And then this complex token is fed back into this, very similar to what you see here. So now you have Valpik offers many direct integrations that allow you to build. This is the input at time step 0. At time step 1, when the first token has already been generated, then the input will actually be Valpik offers many direct integrations that allow you to build complex. And then it goes through the entire model, and then you get a new output and a new probability distribution across the vocabulary. And now some other word may have a higher probability than complex, and therefore that word will be generated and not complex, right? So that's the simple way, or a simple and easy way to understand how this token generation is happening at each time step. That's the most obvious, simple way. But now you can try and make it more complex and decide how to generate different kinds of tokens. What are the strategies that you can follow? And that's really what is happening when you do token generation. So just to give you a high level overview, there are several ways in which you can control the text generation, right? In the end, the LLM is capable of producing probability distribution across several tokens, across several time steps. And now the whole point of controlling the text generation to get what you want, right? Let's say you are trying to predict the sentiment of tweets. So then what you're looking for is, hey, is this tweet positive or is this tweet negative? In another case, you're trying to summarize a document. So you're trying to, make the information concise. So in each of those steps, what you're trying to do is control in some shape or form the text that is generated. You saw how the text is generated now, and now what are the ways in which you can control the way in which this text is generated? There are three broad categories of ways in which you can control this. The first is called technical parameters, the second is called model parameters, and the third is called context parameters. It gives you a high level overview. At the moment, and also now with the quality of these text generation models, we typically focus only on the third part, which is the context parameters. That means that most of the time we can get what we want, so we can control the text generation by simply designing the prompt appropriately, which is also called prompt design. And that's what we are going to do in our project as well. But it is useful to know what the technical parameters are and how they can be adjusted, and what the model parameters are and how they can be adjusted. You may not use this in your project itself. You can do it if you want, but this gives you a very good sense of what is actually happening under the hood. And most LLM APIs, including OpenAI, Cloud, and so on, have already optimized this to a large extent. So they control it and have found the right set of parameters for it, so that all you need to do is design the prompt. And designing the prompt is, of course, the easiest thing to do, because you're just manipulating English, right? So you give it some instructions, and then you can change the instructions and stuff like this. Whereas controlling technical parameters and model parameters is what we would have done, let's say 4 years ago when GPT-2 was launched and we were using it. Then you had to kind of make use of these technical parameters in order to control the way the text was being generated. And that was less helpful than, let's say, ChatGPT is right now, right? So just wanted to set the context for that. We will look now what we mean by these technical parameters and model parameters, and kind of show you how it really works under the hood. So let's look at the first one, right? So yeah, like I said, you can follow along with the notebook, which is part of the course material. Each of these methods is actually explained there, but I also provide a graphical representation here to kind of explain the concept to you. So the first thing that we can think of is greedy search. That means that it's the most simplest and obvious path that we can take to generate tokens. What does that mean? It means that given an input, so this is the input sentence that we had, Vulpix offers many direct integrations that allow you to build. And then it goes into the model, and now you are at the token generation 1, right? So you are trying to generate the first token that will come after build. That's what you're looking to do. And at this point, you have several options. As I said, that's nothing but the probability distribution. But you pick the one which has the highest probability, right? So what you see here is the top 5 options at this particular time step. So the token with the highest probability is your, then the second highest probability token is the third highest probability token is and so on. And you pick the one with the highest probability. Makes sense? It's obvious. So that's what you do. In the second token generation step, so now you've already generated you take this put it back into the input, and now you're trying to generate the next token after that, which is token 2 in this case. And now the probability distribution changes because the input has changed. It doesn't make sense that you are generating your, for instance, right? So the probability distribution changes, and the word that should come now, the one which has the highest probability is own. The word with the second highest probability is app. The one with the third highest probability is business, and so on. But again, very simply, what do? You just pick the token with the highest probability at this time step, which in this case is own. And now you keep repeating this exercise at each time step. Or token step. So you can see now how it is progressing. So you kind of see that in this way, you've kind of completed the sentence by picking at each time step the token with the highest probability. And now your sentence becomes, Vulpix offers many direct integrations that allow you to build your own custom apps, full stop. Note that full stop is also its own token, right? But that's quite simple, quite obvious, and you would be like, yeah, sure, I think that's the best way to kind of do it. Why would I choose to pick a token that has a lower probability when something else suits better, right? And I would completely agree with that, except now you change your thinking a bit to not just pick a token based on its probability at that time step, but try and aggregate it over multiple time steps. So what do I mean? That's kind of what is implemented by what we call as beam search. That's the next one. So in the earlier case, what we said is I am only concerned making a decision based on a time step. right? I don't care what came before. I don't care what comes after. I just pick the token that fits the best or has the highest probability at that time step. But sometimes actually you may get a better fit or a better overall probability if you consider the total probability across different time steps, right? So that means that in this case, for example, that is what beam search does. It maintains a certain number of sequences, which is also called as number of beams, in memory. So it kind of stores the options for, let's say, 3 of them. In this case, it stores the options for 3 types of completions, right? So there are 3 possible sequences. And in the first case, I just pick the top 3. So the top 3 with the highest probability, then I expand that out. And so in the second time step, I kind of have 3 sequences, and each of those sequences can have a different collection of tokens. It does not necessarily need to be the highest probability token at each time, but I maintain this sequence now. And what happens when you maintain this sequence now, as you see here, if I had gone with just the highest probability at each time step, you would just pick your own custom apps and so on, right? So you would pick the one which has the highest probability. But now what really happens is, because you've kept this kind of number of sequences in memory, you end up discovering sequences that have a higher overall probability across time steps. So because the probability gets added over each time step, you want to optimize for the best completion or the best overall probability across different time steps, rather than restricting your decision purely based on the only time step that you're looking at. So that's kind of what is meant by beam search. That means I optimize for overall higher probability rather than the probability only at a given time step. And therefore what you get in this case is an option like Vulpix offers many direct integrations that allow you to build your own apps and services, right? So it becomes a slightly nicer sequence as compared to what you might have got if you had just picked the highest probability. And of course, there is a drawback, which is the fact that you need to maintain this number of beams in memory, right? So you need to keep storing it, you need to keep accumulating the overall probability, and at each time step compare it, and so on. So there is an additional computation that is required as compared to the previous one where you just pick the highest probability. But these are different strategies that the LLM providers follow in order to generate text completions that are more desirable, that are more nice, right? So that's kind of what I mean by, by changing these parameters, you can kind of figure out what is the best kind of token completion sequence. This is not the only way that you can do it. So now you can kind of start seeing a pattern that at the end, now this is token traversal, right? So you have a bunch of options and you have a different bunch of options at each time step. Now it's all a matter of picking the right set or combinations of tokens that maximize the overall probability, make it look nice and stuff like that. So the one was just the token traversal. In the second case, in this one, for example, there is top K and there is also top P, which I will just look at in the next slide. But in this case, what you're trying to do is you are now trying to restrict the number of tokens that you consider in your options, right? Because as such, the vocabulary of these LLMs is really, really large. So something like BERT, for instance, had a vocabulary size of 650,000, if I'm not mistaken. But something like GPT-2, GPT-3, the number of tokens, it goes into the order of millions and trillions of tokens. So that's the amount of vocabulary that it has. And now, if at each time step, you are kind of going to look at all of them, like the distribution of across all these tokens, it doesn't really make sense, because most likely you're interested in the top 20 or top 50, right? And the others are all a long tail, so they actually don't even matter. You will likely never pick the 50th or the 100th token because it doesn't make sense. It might make sense if you have very long token completions, etc., etc. So that's the strategy now. So how do you optimize for what set of options do you pick from? And that's where the top K comes in, where you say, I want to pick only from the top 20 tokens at each time step, right? So I'm not interested in any token at any time step that is beyond this 20. Give me only these 20. From these 20, I will pick. So that's an example to restrict the computation complexity of this particular method. And the alternative to that is called top P. And here we don't restrict by number, but we restrict by probability. So in the earlier case, we said, hey, I only am interested in the top 20 tokens. But instead, what you say over here is, I'm interested only in the set of tokens that cumulatively add up to a certain probability value of 95% or 90% or something like that. So the top P value is always specified with the probability value 0.9, 0.95. So you take the sum, so you arrange all the tokens by their in the order of their probability, and you pick those set of tokens till which cumulatively they reach a 90% probability distribution. So this long tail, extremely long tail of these small probabilities is ignored. So you kind of are able to adapt at each time step, because in the previous case you would pick only the 20 at each time step, but in this case maybe in the first time step it is the 20 top tokens that add up to the 90%, but in the second time step it might be the 30 top tokens that add up to the 90%, and this can change at each time step. So that's sort of what you're doing with top K and top P to kind of reduce the complexity of computation by considering only a fewer number of tokens, which you would say are the most important tokens. A really cool thing to note is that even today in the OpenAI API, there is a parameter called top P that you can actually decide. So when you're making the API call, you can actually say what should be the top P value that you want if you want to control it, right? So while all of these are kind of optimized already by the LLM providers, you still have the ability to kind of modify it, manipulate it, so that you can control the text generation. That's the whole goal over here. Of course, over time, there were several different kinds of token traversal, token selection methods that came in. Another example of this is called contrastive search, which is very, very important for longer token sequences. When you go through the accompanying notebook, you will see that especially a model like GPT-2, if you ask it to generate a slightly longer text generation, it starts repeating itself. It kind of, gives you the same tokens again and again, and that's typically a result of the way the greedy search and beam search works. And in the sense that this is called as, a degeneration. So that means that when the text gets longer, it starts degenerating because it is not making sense anymore. And that's where you have something called as a degeneration penalty, which means that you try and introduce a parameter called alpha, that is the degeneration penalty, which is applied and make sure that the token that gets generated is quite different from the token that came before, or the set of tokens that came before, right? So what used to happen was when you generate longer sets of tokens, the style and the actual tokens were very similar to the ones that came before. So that's why you start getting repetition. And so you introduce a parameter called degeneration penalty. You start manipulating the values of this so that the tokens that are generated in the future are quite different from the tokens that came before it, right? So you are manipulating the probability value of these future tokens based on the previous tokens, and as a way to kind of distinguish them and make it more unique and so on. Another parameter that again you might have heard of quite often and that you will come across is a temperature parameter, which works very similarly to the degeneration penalty. Again, a higher value of temperature makes the generated tokens, or the probability distribution of the generated tokens, very different from the tokens that came before it. So it becomes more creative. It goes into a larger token traversal space. Instead, if you have a temperature value that is lower, then the token traversal space reduces. It generally picks those tokens that have a higher probability, and they have a higher probability, so they kind of follow much more closely what came before. So they agree a lot more to the tokens that came before, and therefore get less creative. So this temperature parameter can also be seen as a creativity parameter, which is again nothing but how far does their token traversal go, or how much there is randomness in the token that is generated. So at the end, all these parameters still exist. So the temperature parameter, for instance, is also there in the OpenAI API. So that's why it's useful to know what is actually happening under the hood, what really happens when you change temperature, what happens when you change top P, and stuff like that. This is not the only way in which you can control text generation. So, these are parameters, there are tokens already there, and you can then control, should I pick this, should I pick that, what is the strategy to do that. But another way to control text generation is by fine-tuning models, right? So, for instance, you can kind of want the token to be generated in a certain style. And so what you do by fine-tuning it is by allowing it to look at data that is structured in a certain way. Let's say that you write in a certain style, third person or something like this, and let's say you have a lot of data that shows this. You can actually take an existing model like GPT-2 and fine-tune it on this new style, and then it will start generating tokens in this style, right? So this is very different from token traversal that we looked at so far, because here you're actually going in and changing the weights of the model, changing the parameters of the model, you're training the model. So you are actually making changes in the model itself, and therefore controlling the way in which the text is generated. Whereas in the token traversal methods, you don't do anything to the model itself. The model, the weights, the parameters, they're all frozen, and all you're doing is changing the way the tokens or which token is generated. You're just controlling that. You don't touch the model itself. But in this case, what you do is, you fine tune it to suit a certain style and so on. Or another example, this is something that Salesforce did with their model called Control S, which is that they added some control tokens while training the model. So what they did is they went to Reddit, they crawled several subreddits, and they used the name of the subreddit, or they defined a category, for example, a category like computing, a category like science and technology, a category like health. They created this control token, and while they were training the model, they also specified the control token. And then what happens is, at the generation time, if you specify this control token, it then generates text in that particular style or agree to that particular topic. So if there was computing, then all the text that will be generated will be all around computers, software, IT, stuff like that. And if that control token happens to be health, then it generates tokens that are more in that direction, right? So this is another way to control text generation, and all of this was done before ChatGPT, right? So before everything that we saw, these were various ways or techniques by which you could influence the way that text would be generated. In the previous example, by controlling the token traversal. In this example, by actually going in and changing the way the model is trained itself, so that you can then at inference time control which parameters are there, control which tokens are there, and stuff like that. So it's just very interesting. All of this is kind of redundant now, but it's very useful to see again how we got here. And we got here is where we are now, which is prompt design, which is today most frontier large language models, so GPT-4, GPT-4o, Cloud 3.5, most of them, you can control the token generation simply by adapting the prompts, right? So for instance, you can say, hey, please summarize this, and you give it a piece of text, you ask it, please summarize it, and then it gives you like a long summary, and then you can adapt the prompt to say, please summarize it in 2 sentences only, and then it will understand this and then provide you only a 2-sentence summary. In most cases, it will follow the prompt that you have said, or the English that you have written. It will be followed, and that's the best way to work with an LLM. That's what we're going to do as well, simply because that makes life easy, instead of then fine-tuning all these parameters and stuff like that. If you see that the prompt is not working, then you can also go one step further and start modifying the stop p value and stuff like this. But for the most case, you can very easily condition the text generation purely based on the design of your prompt. And that's what I show here. For example, in this case, this is GPT-2, so it doesn't work as good as GPT 3.5 or whatever, but I'm sure if you try it out, it will be the same on GPT 3.5. You can condition it on RBOK. So I just say, in this case on the left, I say RBOK offers many direct integrations that allow you to build, etc., etc. And then I can say RBOK offers many direct software integrations that allow you. So I've just added an additional token called software, and then it also adapts the way the text is produced to generate more tokens like software or in the direction of software. Whereas here, I didn't specify anything about software and it went into instrumentation, etc., etc. Whereas here, it says go into solid workflows, editor, notifications, so these are all tokens that are related to software. So, of course, this is GPT-2, so it's not the best model out there, but the reason I use GPT-2 in this video and also in the accompanying notebook is because GPT-2 is open source, and that means that you can fix all the parameters of this model. Otherwise, every time that you call, let's say, for instance, the OpenAI API, each time that you call with the same prompt, you might get a different response back because there is a certain element of randomness. So you cannot be sure whether the change in the response was because of the change that you made in the prompt or because of the randomness. So that's why we pick GPT-2. It's open source. We fix all kinds of random parameters that can change. So different seed values at the GPU level, at the CPU level, etc., etc. So you will see this in the notebook in order to fix the way a model works. And then all the changes that you do are the change, and therefore, and the results that you see are a result of you kind of making the changes. And so you can really observe what is actually happening, right? Right. So, that's just to say, to conclude that there are a lot of ways in which you can control the text generation. The simplest way is by designing the prompt to do it for you. And the more complex way, which is actually happening under the hood, especially by the LLM providers, is these other parameters that we saw so far. But our focus for most of your tasks in general, it's enough to know prompt design. It's enough to kind of add instructions to your prompt and so on. Now, when designing a particular prompt, it is important that you think of it with a certain structure, or at least I find this very helpful. Prompt design is not a science, but is still kind of evolving. I would say it's more like an art form and something that you need to build familiarity with. And therefore, I always like to start with a principle or a framework, and that's what I present here, which is a framework that I use. It has 4 steps. You may choose not to use each and every step, but I think if you largely understand this, you can start creating your prompts using this kind of framework. What is the framework? The first one is context. That means that I ground the LLM by directing it towards specific aspects of its world knowledge that you would like to leverage. And I think it's best if I show this with an example, because then it becomes much clearer. So this is an example prompt that uses the same framework as what we saw before. So the context says, you are a startup consultant who helps founders get to real results fast. The focus is on quickly iterating with the product and gaining valuable feedback, right? So I am using this prompt as a way to get into a brainstorming exercise with ChatGPT, but as a starting point, I always set the context to kind of ground the model in a particular area of its world knowledge. Because the LLM has been trained by using the text from the whole internet, it actually knows a lot about a lot of things. And you want it to focus or derive insights or generate tokens based on a particular area. Just to contrast it with the controllers example, that they use this control parameter, which says accounting or computing or health or something like that. And this is our way of doing it in the prompt itself. So you set the context saying you are a startup consultant who helps founders get to real results. The moment you set this up, the LLM starts generating text based on a certain area of its world knowledge. And that's kind of what you're hoping for. The second one is the task or the instruction that you want it to do, right? So what is it that you want it to do? What is the task that you're giving it? And again, here, if you follow instruction patterns that are similar to the data set that it was instruction fine-tuned on, this again is very helpful, because then you are sort of doing it in the same way or based on the same data that it has already seen while it is being trained, right? So you can use words like give me guidance or tell me or can you help me, and things like this. So given your expertise in strategy and coaching startup founders, I want you to give me guidance on how to proceed. So there are a lot of how, give me guidance. So these kind of questions, which is what you would expect in a typical instruction fine-tuned data set. So that's again linking it back to how it was trained in the first place. The third one is input data. This may or may not be necessary because this is where you have to augment the data capabilities of the LLM, right? So the LLM has been trained on a certain data set, which will likely not include data set that you are privy to. Maybe you have your own blog or you have your own PDF that likely was never on the internet, or you have an Excel of data of some form, etc., etc. So input data can be varied, and it may not be something that the LLM has seen before during its training time. And so this is the place where you would insert the input data. For instance, in this case, I just say I want to create a landing page for my startup. I want it to be attractive. I have been told that Webflow and Framer are possible websites that can help me achieve this, right? So the fact that Webflow and Framer are quite new, they're tools that help you, no-code tools that help you design websites, may not be something that the LLM actually knows about. But you're just giving this as additional input data that the LLM doesn't know. It could be an Excel file, it could be PDF, etc., etc. And lastly, what is the output format that you want? And again, the output format can be, in this case, for example, I say, hey, I want this to be a conversation and I'm looking for you to guide me towards the perfect design for my website. So I want it to be a dialogue. You could also say, hey, give me a JSON response if you're doing some kind of a text extraction exercise. You could also say, answer only in one word or answer in maximum of 2 sentences. So you're trying to adapt in the way in which the output is presented to you. And that's what I mean by the output format. Again, it's a sort of instruction fine-tuning data set because you are kind of giving it an instruction and providing it with examples of how it should respond and things like that. So I find this as a general structure very useful for me to think about how I compose my prompt, and hopefully that we will see an example of this when we do the project, because that's how we will shape the prompt for our project as well. So just to also give you some additional tips and tricks, the reason why you use context is to improve the grounding of the model by asking for experts in the field. So you can say, if you're interested in physics, you can say, act like Albert Einstein and based on this, explain to me, or act like Richard Feynman and explain this concept to me. You can actually do this. The task or instruction can be improved by the help of certain keywords like think step by step, which is also called chain of thought. You can also prevent hallucinations in this way by saying include references or reliable sources. So it actually tries to think in a much more structured way. When you talk about input data, one of the most common use cases of LLMs is a class of application called retrieval augmented generation. We will not do this or focus on this in this course itself, but it's a way to provide additional context so that the LLM can then reason based on that context. A perfect example of this would be that if you are working at a company, you typically have documentation in the form of a Confluence documentation or a Notion page or something like this. This is private to your organization and likely nothing that the LLM has seen before. And so you can actually retrieve certain aspects of it and include it in the context so that the LLM then responds or summarizes that information and that information only, and does not rely on the information that is coming from its world knowledge. And then output format is where you actually want to say, hey, give it to me in JSON format, and you can actually give it an example of what that JSON should look like. There is also an advanced capability called as function calling, which again is very, very useful to kind of structure the way the response comes, which is very useful when you don't, you're not interacting with the LLM in a sort of human way, but in a programmatic way, because you can use the response from the LLM to then call another function because they are JSON responses. And so that's again the way the output format is very helpful. So that's to kind of summarize the way that I would structure or design a particular prompt in order to control text generation, right? Because that is proving to be increasingly the best way to control text generation, or let's say the easiest way to control text generation. The earlier methods that we saw can of course be used, but it's much harder, and the LLMs are continuously getting better to the extent that they can really follow prompts, and this is probably all you need, or as they say, prompt design is all you need. As additional references, just like there are design patterns when you write code, like in Java or any other, so there are common ways to solve certain kind of programming challenges. In the same way, people are also thinking about, are there some common ways in which you can solve some common prompt design challenges, or are there certain categories of prompt designs? And this is a paper, again linked below, which gives some kind of examples, right? So for instance, here you have a persona prompt, and that's kind of an example of what I said by providing the context. So act like Richard Feynman and explain this particular concept to me. You also have a fact check list, for instance, to prevent hallucination. So these are some abstraction patterns that people are trying to think through, and I'm saying trying because it's not yet established what's the best way to do it, and so I don't really rely as heavily on it, but just to give you additional help and resources to kind of think about it. For me, the framework that I presented before, context, task or instruction, input data, and output format, is sort of always my starting point when trying to design a prompt. And then based on how it responds, based on instructions and adaptations and stuff like this, is when I evolve my prompt. But this for me is always a very good starting point. But as I said, feel free to also look at these resources, and there are also additional resources that I have added in the slides. Before ending this video, I also just wanted to say, hey, the next video is going to be about building our own product, which is called Narrative Tales, which is nothing but a personalized podcast generator. The idea here is you typically never have a PDF on a topic that you're interested in. Let's say a new research paper came out, which nobody is actually paying attention to, but you would actually like to, listen to this, and as a podcast and so on, many people actually understand better when you're listening to something rather than reading something. And that's an example of the product that we will build in this course, which is called Narrative Tales, which takes us an input, any PDF document, and produces a personalized podcast in a certain style with certain voices. So really an MP3 file that you can then take with you and listen on your drives, walks, jogs, whatever. So yeah, hopefully you're excited, and we will get to that in the next video.